So with any luck from last year, remember that if you have a position function, you take its derivative, you end up with the velocity function. Take the derivative of your velocity function, you end up with an acceleration function, and take the derivative of that, and you end up with the jerk function, which we won't ever use. You guys all remember what the ones after that are? Just for fun. What comes after the jerk function?
Is it now?
Yes, it is. And then what comes after that? Oh, cool, the chat's not popping up when you guys say stuff. There you go, yeah. Crackle and then pop. For some reason, that's what they decided to name them. Not 100% sure why, but that's what they decided to do. So we know how to go from one of these, from the position to the velocity to the acceleration and so on. We also, I'm sure, remember how to go back the other direction using integration, but we won't worry about that right now. We'll worry about that in a couple of weeks. The one thing I do want you to remember about all this is that speed is the absolute value of velocity. So remind yourselves that speed has no direction to it, whereas velocity has direction. And so, if I say that something has a speed of 5 miles per hour, it means it could be moving to the right, it could be moving to the left, it could be moving in any direction. Whereas if I say that the velocity is 5 miles an hour, we talk about that as a velocity in the direction to the right if it's positive, or to the left if it's negative, or perhaps talking about moving in a line straight up and down, then positive would be up and negative would be down. Everybody good with that? All right, cool. So suppose we have a particle that's moving along a line, so its position is given by t squared minus 4t plus 3, where s is in meters and t is in seconds. We want to find the displacement of the particle and its average velocity and its instantaneous velocity and its acceleration. So a bunch of different things that we want to find. So first off, what's the difference between displacement and distance? Right, our displacement is how far we are from where we start, right? And distance is the actual amount that we traveled. So if we went to the right 10 units and back to the left 10 units and where we were started, we were back exactly where we started, then we'd be having a displacement of 0, but we'd have a total distance traveled of 20 units. So distance is the total amount traveled, and displacement is how far you are from where you started. So if we want to know how far we are from where we started, find the displacement during the first 2 seconds, first thing we need to do is find s of 0, and then we need to find s of 2. So what's s of 0? What's s of 0? Should be 3. Okay, and what's s of 2? Should be -1, right? And so the displacement should be our starting point minus our ending point, which is 4. We moved 4 units. What were they? Meters, probably 4 meters. And which direction did we go? We went from 3 to -1. We found 4 meters to the left. We don't necessarily have to specify that it's to the left, but since we know that it is, we might as well. Everybody good with that? All right. So if we want to find the average velocity of the particle during the first 4 seconds, what do we need to do? Average velocity should be a displacement divided by a change in time, or change in position divided by a change in time. So what's our displacement in the first 4 seconds? We're going from s of 0 minus s of 4. S of 0 is 3, and what's s of 4? Should also be 3. And what's our change in time? It should be 0 minus 4. Right? We're going from 0 to 4. So 3 minus 3 over negative 4, which is 0. So our average velocity is 0 meters per second. Everybody good with that? Sorry, Nick, I missed your question, but it looks like Aiden answered it for you. Sorry, I missed that. Any issues with our average velocity in those first 4 seconds? All right, what about our instantaneous velocity at t equals 4? What do we need to do to find that? To find the velocity function, we need to take the derivative of our position function, which is 2t minus 4, easy, and evaluated at 4 gives us 4 meters per second. Everybody good with that? And if we're going to look at the acceleration, we need the acceleration function. If t is equal to v prime, it should be 2 meters per second squared. Everybody good with that? It doesn't matter what t value we're looking at for our acceleration, because no matter what, that acceleration is always 2. All right. Yeah, back page. There you go. I don't know why it's not. When somebody says something in the chat, it's not like saying anything to me anymore. So I don't know what the problem with that is, but. All right, everybody good with that? Easy enough? All right, we'll do one more real quick. Why don't you guys do this one real fast, and then we'll talk about it. So if we're looking for the velocity, what's our derivative of x of t? What's our velocity function? Derivative of e to the 2t should be 2e to the 2t, and then minus 4t. And if we're going to evaluate that at t equals 2, what does that become? It becomes 2e to the 4th minus 8. And we won't attach any units to that because I don't think I got seconds in there, but that's fine. We'll just say 2e to the 4th minus 8 units per second. Everybody good with that? Okay, and if we want the acceleration, we should be taking the derivative of that, which should be 4e to the 2t minus 4. And if we're going to evaluate that at t equals 3, that should give us 4e to the 6th minus 4 units per second squared. And if we want to find the total distance that this particle is going to move in the first 3 seconds, we should be able to figure that out. Why should we be able to figure that out? Normally, to find the total distance traveled, we need to do what? We'd have to take an integral of the velocity function, right? If we take an integral of the speed function, right? Integral of the absolute value of velocity. But since we're not doing integrals yet, how can we still find the total distance the particle moves in those first 3 seconds? We should be able to just think about what the graph of our velocity function looks like. So I've graphed it on Desmos. Let me show you the graph of it. And from t equals 0 to t equals 3, this is the velocity function. What can you tell me about the velocity? Velocity is always positive, right? And if our velocity is always positive, then that means that this particle should always be moving to the right. So if it's always moving to the right, then we should know that we don't need to worry about the direction that it's moving. And if it's always moving to the right, then that position is always increasing. Should never be going back towards where it started. And so we can just then go back in and say v is greater than 0 for the interval from 0 to 3. And so we can just find the position at 3 and the position at 0 and subtract them. X of 3 minus x of 0. What's x of 3? It should be e to the 6th minus 18 plus 2 minus e to the 0 is 1 minus 0 plus 2, where we end up with e to the 16th, where we got minus 16 minus 17 minus 19. Did I do my arithmetic right there? I think so. E to the 6th minus 19 units. Everybody good with that, and why we don't need to worry about speed for this particular one? Oh, yeah, e to the 6th. I don't know why I wrote 16th down there. That's weird. But yeah, definitely e to the 6th. I wrote that the first time, right? Yeah. E to the 6th minus 19. Sorry about that. I don't know where that 16 came from. Must have already been thinking about negative 18 plus 2 or something. Everybody good now? All right. Okay, everybody, any questions on motion in a plane? Minus 15? I don't know, I thought I did that arithmetic right. You got negative 18, you got a plus 2, you got minus e to the 0, e to the 0 is 1, and then minus the 0, and then plus the 2. Yeah, I think it's minus 19. It's all right, Luke. All right, everybody good with that? All right, so now rather than just looking at particles that move in a straight line, we're going to look at particles that are moving in a plane. So rather than just having the option of moving directly to the right or directly to the left or directly up and directly down, they can move at any angle on the plane. And normally when we talk about moving in a plane, we talk about these particles moving in a plane as vectors. So now we've got an infinite number of different directions that our particle can travel at any angle that we still measure going counterclockwise from the positive x-axis. Right, so this angle here is still our angle theta. And so we talk about a two-dimensional vector is just an ordered pair of numbers, a comma b, that we write with these angled brackets, and that's what those are called, is angled brackets. And we call the two different pieces of it the a component, which is our x component of it. They're called components, and we call the a component the x, and the b component is the y. And the vector, when we talk about a vector that's the standard representation of a vector, we talk about the vector that's going from the origin to some point, some ordered pair a comma b. That vector is the vector ab. And so that's what we've got drawn there, is the vector ab. Vectors don't have to start at the origin. Just the standard representation of them is from the origin, and generally we'll deal with them starting at the origin. But we might have some that don't start at the origin, and we have to combine them with ones from the origin to find the resultant vector. But we'll talk about that when we get there. So a couple of little notational things is that we have what's called the magnitude of a vector, which is also sometimes written as the absolute value of a vector. It's just the length of that arrow. So it's just the distance formula or the Pythagorean theorem on that vector AB. So it's just the square root of a squared plus b squared. So if we're looking for the magnitude of a vector, or if I ask you for the absolute value of a vector, it's just the square root of a squared plus b squared. We also have what's called the zero vector. Zero vector is just the vector 0, 0. It has a length of 0 and it has no direction to it. So if we talk about a zero vector, we don't need to attach any directional angle to it. And then the direction of a vector is the smallest non-negative angle. That's this angle right here, formed with the positive x-axis and the vector. So we've got our theta already written there. Everybody good with all of those basic things about vectors and sort of what they are? It just represents how the particle moves as it goes from, let's say, the origin to this point AB. We'd say it moves along this vector. Good or no? All right. So as I said a minute ago, not all vectors start at the origin. It can begin and end at any point in the plane. But if the vector has the same length and it has the same direction, then we say that they are equivalent vectors. So vectors u and v here are equivalent vectors because they are both going up 4 and over 3 units. Even though they start in different places and end in different places, they both have the same length and they both have the same direction to them. Right? So they both go up 4 and over 3, or over 3 and up 4. So those are called equivalent vectors. We have a rule, it's called the head minus tail rule, that if our vector, if our arrow has an initial point of x1, y1 and a terminal point of x2, y2, it just represents the vector x2 minus x1, y2 minus y1. Everybody good with that? It's all just like the kind of basic things that you should have learned probably a couple of years ago about vectors. Any issues with any of that? All right, so let's see if we can find the magnitude and the direction of the vector -1 root 3. So first off, how are we going to find the magnitude of that vector? Should just be the absolute value of that vector. And the absolute value is just the square root of a squared plus b squared, which should give us square root of 4 or 2. So this vector has a magnitude of 2. And how are we going to find its direction? Any ideas on how we might find its direction? If our vector has an x component of -1 and a y component of root 3, that means it's going, here's -1 and here's root 3. It's going from here to here, right? There's our vector, -1 root 3. Okay. And how are we going to figure out what that should be? Anybody know how to do that? You guys can all still hear me, right? Oh, you're all typing in the chat and it's just not telling you that you are. Okay. Gotta get this Zoom thing working right. Yeah, it's a tangent. It's an inverse tangent. So Shayla, you said tangent, yeah, inverse tangent. So we're going to do the inverse tangent of our y component over our x component. And so when we do that, what do we end up getting? What's the inverse tangent of -√3? So it should be negative pi over 3, right? But we know that this vector is in which quadrant? It's in the second quadrant, and so we're looking for this angle right here, which has a reference angle of pi over 3, which should give us a direction of 2 pi over 3. Does that make sense to everybody? All right. And how will we find the component form of a vector that has a magnitude of 4 with a direction angle of 30 degrees? Any ideas on that? Yep, we should just be able to use the same idea that we've been using for polar, that x should be equal to our r value or our magnitude times cosine of 30 degrees, and our y value should be 4 times the sine of 30 degrees. And so this should give us what? 4 times root 3 over 2, and this should be 4 times a half, which will give us a vector of 2 root 3 comma 2. Everybody good with that? That's the very, very basics of vectors. We're going to stop with that because we're pretty much out of time. We're going to talk about some rules for vectors next time, and then we're going to actually do some calculus work with them.